All right, let's talk about compounding monthly, quarterly, semi-annually, or daily cases with this slightly bigger formula. Now, but I did say that we're using a different formula for compounding annually. But if you think about this, let me go ahead and add something over here, okay? If you have compounding annually, that means it's going to get compounded once a year. So n will be 1. So take a look. If I plug in n equals 1 into this formula, a equals p times 1 plus APR divided by n, right? Divided by n. N is 1. And we're raising that to n times y power. N is 1 times y power. What happened? This will just turn into p times 1 plus, because APR divided by 1, anything divided by 1 is just going to be itself APR raised to the same thing over here, 1 times y. That's just going to be y. So, I mean, I say there are different formulas, but it's just the same one. But when n is 1, n equals 1, if it's compounding annually, then this bigger compounding formula with n being replaced by 1 just turns into what we used on our previous page. So it's really the same formula. Now, but let's look at example 3 together, where I have A, B, C, and D, and I think they're all different cases. So we'll use this big formula, but you will want to have a scientific calculator for this, okay? All right, use the appropriate compound interest formula to compute the balance in the account after the stated period of time. A, $12,000 is invested for 5 years with an APR of 6%. I'll go ahead and convert that into 0.06. But look at this one. They said quarterly compounding. Quarterly compounding. So you will need to make a note that this means n equals quarterly. Use n equals 4. Now we got everything we need to figure out the amount accumulated after 5 years. So let's plug it into the formula we know. A equals principal times. So do 12,000 times 1 plus, do APR over n, 0.06 divided by n is 4. And then if you be careful over here, we're raising this to n times y power, okay? N is 4 and y is 5. So you will do 4 times 5, and that's going to be the power, okay? So let's go ahead and type this in our scientific calculator together. And for those of you who does have this percent symbol, you can type in 6%. But let me go ahead and type this in my calculator. I just want to show you how I do that. So I'm going to go to my app, a calculator app, and then type this in. So 12,000 times 1 plus, and I need a fraction where I put 0.06 for the 6% for the numerator, and the denominator is 4 because it's quarterly compounding. And we're going to close that parenthesis and raise that to 4 times 5th power. If I hit enter, I will get that the answer is the amount after 6-year investment will be $16,162 and, oopsies, I gotta look at all these ads because I'm using the free app. Maybe I'll buy one soon. All right, so the answer is $16,162.26. Okay, using that compounding interest formula. Now, it's really going to be the same thing. For quarterly compounding, I just have to make sure that I plug in 4 into n. But the other one, let's say B, we just have to look for that keyword. So say this one, they want you to do daily compounding. So you know for this one, your n will be 365. So let's do this one. So $18,000 is invested for 5 years okay, with APR of 4%. And we're doing daily compounding. So A equals, we're going to do 18,000 times 1 plus APR. APR is 0.04, and we're going to divide this by what big number? N is 365 this time. And then we're going to raise this to N times Y power. That will be 365 times 5 year. So we're really raising this to how many days do we have and how many days do we have in 5 years, okay? So let me go ahead and type this in my calculator. I mean, now I use this app pretty often. I'm really thinking about how much is this app? Well, 18,000 times, oh, not cosine, 18,000 times parenthesis 1 plus denominator, I'm sorry, a fraction where I put 0.04 on the numerator, and let's put 365 for daily compounding. And don't forget to raise that to 365 times 5 year period. All right, so if I hit enter, I will see my answer. Maybe after an ad. All right, so we got the answer. The answer is $12,985 and, well, 008. So I'm going to round that up to 1 cent, okay? Alrighty, so let's write the answer. $21,985.01. All right, doing good. Now, I got 2 more, but they're very, very similar. So I'm going to go ahead and just do one and maybe ask you to try the last one yourself, which is, back to quarterly compounding. All right, I'll just do C and then I'll go to the last page. Now, we have $8,000 invested. Notice this time it is Notice this time it is monthly compounding. So for monthly compounding, what is your N value? N is 12, okay? So $8,000 is our principal. We're going to invest that for 19 years with an APR of 5%, 6%. So, by the way, please try to, if you're ever having issue with the class, like if you're still working on project 1, if you need more help, and project 2 is coming up too. So if you ever want to talk about those things, I'm saving our class time to schedule our Zoom meetings, and I've been getting more Zoom conferences with you guys. But feel free to, because I feel like, well, you always email me, so that's really great. But we can always have our Zoom conference, either individual or group. So if you're interested, you just reach out and let me know, and then we will set up something, okay? All right, 8,000 times 1 plus APR of 0.06, and we're dividing this by N. And here for monthly compounding, our N value is 12. And we're going to raise this to N times Y power. So that will be 12 times Y, 19. So the exponent is going to be how many months we have in 19 years, okay? So ready to type this in our calculator? Let's do that together. Alrighty, calculator app. I'm going to go ahead and type in 8,000. It's a smaller amount compared to the first 2 that we did. But since we are waiting for 19 years for this investment, I feel like this money is going to grow a lot. Divided by 0.06 plus 0.06 divided by 12. For monthly compounding, and we're going to raise that to 12 times 19. Okay, so what's going to be the answer? It's 24. The answer is $24,943.19. So, for these compounding, monthly, daily, quarterly or semi-annually cases, just gotta make sure that you're using the right N value. For monthly, use 12. For daily, you're using the big 365, right? And for quarterly, you're going to use 4. We didn't look at semi-annually, but it's going to be the same thing. Use 2, okay? I'll skip D because we did an example of quarterly before. But now let's go over the very last page. Very last page, where we're talking about whether is it an exponential or linear growth or decay or increase or decrease. So I got about 4, but maybe if I can just do 2 and then actually look at the other one yourself. But let's see. Gotta tell you the difference. How do we tell the difference? And I think I put this one on the attendance quiz for Monday. Linear growth occurs. Linear growth. And we worked with this in chapter 5. Linear growth occurs when quantity grows by the same absolute amount in each unit of time. So either you're adding a number every time to get to the next number or subtracting a number to get to the next number, okay? So you've seen an example, you graphed it, you did all sorts of things with it. Say that if you have an XY table, 0, 1, 2, 3, and if you're starting with 5, just making up a random number. And let's say the next number is 11. Next number is, let's say, 17. What's going to be the next number? It's going to be what? 23. Now, let's see what the pattern is here. This is an example of linear growth. You notice that we're going up by, what did I have to add to get to 11? 5 plus 6 got me 11, right? Now, that constant growth, that's what they mean by the same absolute amount. It has to be the same in a linear growth. So if I add another, 11 plus 6, I will get 17, right? 17 plus 6 will give me 23. So that's an example of a linear growth. This is a linear growth. And what do we call that 6? 6 is the constant rate of change, right? It's called a slope. But now we're going to look at a different type of growth or decay, something called an exponential. So take a look. Exponential growth occurs when quantity grows by the same relative amount, that is by the same percentage in each unit of time. Now, for example, what if something grows by 100% every time? So let me give you an example, but this will be a exponential. Say that we're from like 0, 1, 2, 3. Say that we're starting with 1, okay? And then I'll say the next number is 2, okay? And you may think, well, it's just adding 1. Didn't you just add 1? But no, I'm not going to add. I'm going to say that the next output will be 4. Ooh, what's going to be the next output? The next output will be 8. Now, this is an example of an exponential growth. And you can see that adding rule doesn't apply because, the first one, if you're looking at adding rule, I added 1. The second one, what? I added what? 2. The next one, I added what? 4. So that's not the constant rate of change. This isn't a slope. We don't have a slope here. This isn't a linear growth. So, but what you notice is this. From 1 to 2, what I did, I really just multiplied it by 2. Because, guys, if you think about this, doubling something is increasing the original quantity by, 100%, right? The next one, I also did 2 times 2, and that's how I got 4. I also did 4 times 2, and that's how I got 8. If you see this is going to be an example of something like this. It's going to be an example of exponential growth. And my example was pretty obvious because I was multiplying by multiplying by a number. A number was easy to see that it was just 2, but it doesn't have to be just simply doubling. It may be multiplying by, let's say, like 0.6 or 0.7. So we'll look at those cases, but the relative amount, if it says it's growing by the same relative amount, you can think of it as it's growing by the same percentage in each unit of time. So we're going to look at, I think we should. We should look at all 4 examples here and decide whether they are linear or exponential. And we're going to try to answer the question, okay? A. The population of a town is increasing by 641 people per year. This isn't relative amount. This is absolute amount. Every year, the population is going up by 641 people per year. So because the quantity is growing by the same absolute amount, we would say this is a linear growth. This is a linear growth. We answer the first part. Now what else? If the population is 1,100 people today, what will be the population in 4 years? Now we can figure this out, right? That's the beginning. So I'm going to go ahead and use a calculator, but of course we can set up a, We can set up a linear function to figure this out. But I'm just going to do it the basic way. If I'm growing by 641 people per year, to get to the next year, this is now. I'll just label this so that this is now. And this is in 1 year. If I add 110 plus 641, I will get 1741. Okay? I'm going to add another 641, and that will be the population in 2 years, right? That plus 641 is 2382. And then I can do 3-year population will be, you add another 641. You see how this method will work okay if we're just looking at the near future, right? But if you're thinking about 400 years, we don't want to be sitting here adding 400 or 641s. That's where you're going to probably pull up a multiplication. Now, but I was able to figure this out. This wasn't too long. I can say 4-year period. I'm just going to add another 641. And the final answer that I wanted was 3,664. Oh, let me make this a little bit smaller. So that's what you can do. The final answer is 3,664 people. But if you want to set up a linear function, it will be something like this. Y equals what? What's the constant rate of change? 641, right? Times x, where x is the number of years, plus what's the y-intercept? Well, now if you think of that as year 0, it's going to be 110, right? If our input is after 4 years, you can plug in 4 into your x, and evaluating this is going to give you y equals 3,664 people. So this is how you can use the slope-intercept form or the linear function to find the answer. But well, that's what we kind of did. We added 641 1, 2, 3, 4 times. That's this part right here, 641 times 4. And then we added that to 110. So either way, we'll work just fine. But let's look at a couple more. All right, the price of a computer component is decreasing. Oh, look at this word. Decreasing at a rate of 10% per year. Now, what does this sound like? Does it sound like an absolute amount or relative amount? This is relative, right? Because when they say 10% per, 10%, because if you think about it, 10% of $1,000 is different from 10% of $5. This is a relative amount. So say that because this is relative amount, this decrease is exponential decrease. Now, I'm going to do this the longer way first, but I will also give you an equation that we can plug into, okay? So now, how much is the price now? This price, well, the component cost $120 today. What will it cost in 3 years? So let me do 1 year first. 1 year. Well, listen, think about this. If it's going decreasing at a rate of 10% per year, it's going down by 10%. We're going to have how much left? 90% left. So I'll do it this way. I will multiply this by 90% or 0.90 to figure out the price price after 1 year. So if I do 120 times 0.9, I will get $108. because if it's going down by 10% per year, 100 minus 10 will give me 90. So I'm going to have 90% of the price, I guess, remaining, or is still worth about the 90% of what it used to be. All right, I'm going to do a couple more. 2 year. And do another times what? 90%. So what is 90% of 108? That's going to be $97.20. Now, they did say, what's the cost in 3 years? So this will be my very last one. In 3 years, I am going to have only 90% of that amount above. That will be $87.48. So that's the answer. Notice this was slightly different compared to the linear growth, but this one, the price is going down, and it was going down by 10% per year. That's why I use 90% to figure out the leftover price, I will say. But okay, now we can try to write, you know what, we're going to do equations of exponential functions in 6.3. So, 6.2. I'll save that for our Wednesday, but try to use this method because it does work okay. It does work just fine. And then I will introduce you the equation part, because I don't think the ones that you're going to get today are going to be like too long. But if it's asking you for 15 years, it's going to be too long to do this method. Let me do one more, because I got to go to a Zoom meeting very soon. All right, I'll do C right now. The value of home is, C is absolute growth. They're too good. I think I really want to cover them all, but I do have a Zoom meeting with one of our classmates at 10 o'clock. So I will be right back, and then I will go over C and D. But if you were okay with what you just saw on example 4, feel free to try the homework problems on My Math Lab, okay? I'll be right back.